Well, last class we talked about the conservation of energy and the work energy theorem. And you know that the conservation of energy is a condition of work energy theorem. Whenever there is no non-conservative forces, when there is no non-conservative force, or even though a non-conservative force or forces are present, they must not do any work. Then only you can conserve the total mechanical energy of the system or rigid bodies. This class will talk about the angular momentum of rigid bodies. Angular momentum of a group of particles is divided into two parts. One, the spin angular momentum, the angular momentum of the system with respect to the center of mass frame, and second, the angular momentum of the center of mass with respect to the given point of reference. You add these two angular momentum, you can get the net angular momentum of the system of particles. Same concept is valid for the rigid body. The angular momentum of a rigid body about a given point, a reference point. Essentially, the reference point should be inertial. The angular momentum of a rigid body about a given point of reference is equal to angular momentum of the rigid body about its center of mass plus angular momentum of the center of mass with respect to the given point of reference. So if you add these two angular momenta, we can get the net angular momentum of the rigid object. That is what we have to write in the form of mathematics. This is a rigid body. Let us assume that the center of mass moves with velocity v of EC with the point of reference. This is the position vector of the center of mass with respect to the point of reference. Spin of the rigid body is omega. The angular momentum of the rigid body about point is given as the sum of two angular momenta, one with respect to the center of mass frame, another is angular momentum of the center of mass with respect to the given point. Angular momentum of the rigid body with respect to the center of mass frame, let be LC, and angular momentum of the center of mass with respect to the given point is called or can be given as LS, where LC is the angular momentum with respect to center of mass frame, and L' is the angular momentum of center of mass with respect to the given point. LC is equal to IC into omega, we calculated, and L' is equal to or RC cross MVC. We studied this concept while we discussed the angular momentum of a point mass. This is a point where entire mass of the rigid body is supposed to be centered. So its angular momentum of the center of mass with respect to the given point is this much. Then we can write total angular momentum of the rigid object with respect to the given point O or P is equal to IC into omega plus RC cross M by C. This does not depend upon any reference frame. So it is called spin angular momentum or internal angular momentum, you can say, and this is called orbital angular momentum. If you add this two, you are getting the net angular momentum of the rigid object. We will take few examples to use this formula. Let us take an example. Let us assume that the disk spins with an angular velocity v by r, where v is the velocity of center of mass. Let us take a point O at a distance of suppose 4r. Find spin angular momentum or LC. Find orbital angular momentum or L dash. Find total angular momentum or LO. Let us solve this problem. The concept is spin angular momentum is IC into omega. If there is a disk of mass m and radius r, IC about the z axis, IC is equal to m square by 2, and omega is given in anticlockwise manner v by r k cap. So you are getting mvr by 2 k cap L spin. So spin angular momentum is outward. Let us find the orbital angular momentum. Is equal to, this is r, this is mv, r cross mv, r cross mv, this is in. So mv r minus k cap mv, this small r is equal to 4r minus k cap minus 4 mvr k cap. Direction factor is very important while you are considering or solving the problems of angular momentum, because angular momentum is a vector quantity. See, total angular momentum is equal to spin angular momentum plus orbital angular momentum. The spin angular momentum is mvr k cap. The orbital angular momentum is minus 4 mvr k cap. If you add, you are getting minus 3 mvr k cap. Answer. Let us take another example. Let us take a rolling object. Rolling body. Fixed a point on the ground. With respect to this point, at the center mass velocity is v. For rolling, angular velocity is omega, that's equal to v by r for rolling. Under this condition, its mass is m, radius is r. Suppose this is a cylinder. K is the radius of gyration. Mk square, that is IC, is equal to mr square by 2. So k square by r square is equal to half for solid cylinder. With respect to the given point, this is the position vector of the center of mass RC cross MVC. RC cross MVC is in, let this angle be theta. Let us first calculate orbital, then spin, then total. Orbital angular momentum is equal to RC cross MVC. That is MVR sin theta. Direction R cross MVC. That is minus K cap. But this quantity R sin theta is none other than the radius of the rolling object. That's equal to minus MVR K cap. So we can write orbital angular momentum is equal to minus MVR K cap. Let us find the spin angular momentum. The spin angular momentum is equal to IC into omega. IC is equal to mk square into omega. Omega is equal to V by R. In which direction? Is given clockwise spin, that is minus K cap. Or you can write M K square by R square into VR minus K cap. Now add both the angular momenta, spin plus orbit, there is a total about this point is equal to minus mvr k cap minus m k square by r square vr k cap. Take common minus mvr k cap. You are getting 1 plus this is the answer, where k square by r square is equal to half. If you substitute, then you are getting minus mvr k cap 1 plus 1 upon 2. That's equal to minus 3 by 2 mvr k cap. This can also be written as L total is equal to mvr minus k cap r square plus k square by r square. R will be getting cancelled and numerator you are getting r minus m v by r r square plus k square. We can just write m r square plus m k square k cap minus. So this is the omega minus omega k cap. This is the IC, this is mr square. IC plus mr square, that's equal to IP. Parallel access theorem. So you can get omega k cap minus omega k cap can be written as omega vector into this can be written as ip. So angular momentum about this point of the rigid body will be equal to angular momentum of the rigid body about this point, instant axis of rotation. So LO is equal to LP is equal to IP into omega. This formula you can apply for pure rolling body, rolling on a fixed surface. You can also apply this formula for fixed axis rotation. For instance, when the body rotates about this fixed axis, you can also use this formula to calculate its angular momentum total. Let us take this example now. Well, let this rod rotate with an angular velocity omega. Its length is L, mass is M. Find angular momentum with respect to center of mass, that is the spin angular momentum. Angular momentum of the center of mass L dash, that is called orbital angular momentum, and total angular momentum, that is about this point P of the pivot. L total for the fixed axis rotation is equal to IP into omega. IP is equal to ml square by 3, and omega is given in anticlockwise manner. That's equal to ml square by 3 omega k cap. Answer. Now come to spin angular momentum, whose formula can be given as IC into omega. We have to take the moment of inertia about the center of mass, ml square by 12. Needless to mention about z axis into omega k cap. That's equal to ml square by 12 omega k cap. Answer. Now the orbital angular momentum is equal to center mass velocity BC. This is R, position vector of the center mass with respect to this pivot or the fixed point. This is R vector or RC vector, and this is MVC vector. R cross MVC. R cross MVC. You are getting outward RC MVC plus k cap. RC is equal to L by 2. M VC will be equal to L by 2 into omega. So you are getting L square by 4 M omega, or ML square by 4 into omega k cap. And you can verify the statement that total angular momentum is equal to spin angular momentum plus orbital angular momentum. If you add these two angular momenta, obviously you are getting total angular momentum. ml square omega by 12 plus ml square omega by 4. You are getting ml square omega by 3. So you can verify that. L orbital plus L spin is equal to L total. We can verify. L orbital is how much? ml square by 4 into omega. What else spin? ml square by 12 omega k cap, and that is equal to ml square by 3 omega k cap. Hence verified. In this way, we can calculate the angular momentum of rigid bodies. Next, we will discuss the cause of change of angular momentum, that is the torque or the angular impulse. And we will prove that the net angular impulse acting on a rigid object will be equal to change in angular momentum of that rigid object, and the net linear impulse, that is the impulse of the net force acting on the rigid object, will be equal to change in linear momentum of the rigid body. All these two theorems are called impulse momentum equation.